Yeah. Red button's the Blaze reporter.
Okay, cool. Thanks. Yeah, thanks, Sydney, for inviting me and having me. I'm afraid I won't reduce the the mortality rate in children, and I won't change solve climate change. So for my presentation, it's about Linux containers, and I would like to talk about the current state of Linux containers without looking at a specific technology or specific implementation at first. Yeah, I have only 30 minutes, so I have to speed up a bit, and I messed up. But here we go again. Okay, containers in a nutshell. I would like to give a quick introduction to containers, or maybe not so quick. Let's see how long it takes. And then I will look into runtimes and orchestration and clustering of container systems. And this slide I showed a couple of times. So in traditional virtualization, we have the hypervisor. So we have first the server and the host kernel and the operating system's userland. Then we have a hypervisor, and we have virtual machines, guests, on top of this hypervisor. And when you look at this shared nothing, shared everything, shared something approach, in the host system or in the lowest layer, we share everything. So we have the same users, or we share the users, we share the kernels, we share the file system, and the operating system takes care of the sharing. On top, between different guests, different virtual machines, they don't share anything. So they are distinct virtual machines, and they have nothing in common, and they cannot communicate or interact with each other. But within the virtual machines, we have share everything again. So we have this machine, so hence the name virtual machine, right? On the lower layer, we have a machine, a physical machine, and on the top layer, we have virtual machines, and they are also, again, share everything in between them. In containers, it's different. Containers share the same host kernel, and on top of the host kernel, we have just distinct kernel namespaces, and I will talk about kernel namespaces in a bit. But if we, and this is, I call it share some things, because you share, for instance, all the kernel namespaces, and as said, I will talk about this, but the kernel technology, the Linux kernels, container technology tries to implement, and I think that's the main goal, tries to implement a share nothing approach, but this is not really solved yet. It's you share something. At least you share the kernel and you share the same system calls. And I will get to that in a bit as well. But if you lift this up and put a hypervisor, so put this Linux containers in a virtual machine, then you have this approach of having a shared everything layer underneath, like in traditional virtualization. And on top you have this kernels or these containers in a virtual machine. And that's how all public container clouds operate, right? So if you have Amazon or Google Cloud or whatever you go to, they don't provide you with bare metal container technologies that you can use. They are all running within virtual machines. So, and I have another view that I like to present here as well, the more interface view. So if you have applications, they are either running directly or they are statically linked and they are running on syscalls directly, or they use the userland and libraries to interact with syscalls. And these syscalls then plug into the kernel, and the kernel plugs into hardware. And in the traditional virtualization case, this hardware is not the real hardware, but it's an emulated hardware. And this, depending on which type of hypervisor you use, then this hypervisor plugs into the kernel, and the kernel talks to the hardware directly. And as said, depending on the technology used for virtualization, this can be different. You can use hypercalls, and you can use emulated devices, and you can have PCI pass-through and all this jazz. But I would like to just blur it and say, okay, you have virtualization magic, and you could have different techniques used to optimize your emulation and make it much faster. But in essence, it's just a layer in between the hardware and the kernel of the guest to emulate the virtual machine, or to emulate the hardware. And in contrast, on the containerization side, we don't have this virtualization magic. We don't have an additional kernel within the virtual machine. We just have the kernel of the host system and the underlying hardware. So all this jazz here, we don't need, we don't have, and hence all the overhead that is introduced by this, we don't have. And in a container, in essence, it's just the application and the userland. So all the libraries and the binaries that are needed for an application to run. And this is just abstracted by different kernel namespaces, which I will explain in a bit. And this is a very lightweight abstraction without much overhead, because the kernel knows about all processes running on the system. Nothing is hidden behind a kernel like this in each guest system, so the performance can be, or all the processes can be scheduled by this one kernel, and they don't have to go through 2 layers of kernels. And this kernel also knows about the hardware layout, and yeah, it can make good scheduling decisions. For instance, if you have 2 sockets here and maybe let's say 12 cores each, if you provide the one guest machine with all the cores you have, they might appear, and in most virtualizations they appear as one socket with 24 cores and not with 2 sockets with 12 cores each. So the kernel in the guest will make decisions upon this layout that he sees, and he won't schedule it perfectly. And then the kernel in the host system has to do tricks and try to optimize the resource scheduling for this virtual machine. So this will hit you hard. Okay, and syscalls is just a security thing. Syscalls in the latest Linux kernel, there are like 300 or 400 system calls, which would be this bit here. And yeah, they were not introduced and they were not created with containers in mind, with different containers in mind. So that's why Linux containers can be, yeah, they say, okay, it's a little bit less secure than traditional virtualization because you do not have this hard barrier of a hypervisor that you have in traditional virtualization. If you can exploit the kernel of the host with a container, then you are root on you exploited the complete system. If you exploit the kernel in a guest machine, then you are only root in the guest machine, and you have to penetrate this virtualization layer as well, which is not that easy because all this virtualization hypercalls and all this was specifically created to make sure that this is secure. So it's less vulnerable as all the system calls. Okay, let's talk a little bit about kernel namespaces. Containers, as we saw, they don't have their own kernel, so they are just a group of processes, and they are isolated by kernel namespaces. The first, or the most intuitive namespace is the PID namespace. So each container, we have 4 here, each of them, they have their own view on the process table that the kernel provides. So normally you have one host, and this host has one process table, and when you create a container, then you get your own process namespace. What does it mean? I'm not a C guy, so I copied this from the internet, but it's pretty simple here. So we clone a child process in this line here, and we clone it with a new PID namespace. And after we clone it, we show the child PID from the view of the host, and within this child, we just show the PID from the view of the child. And as you can see here, the PID of the process that was cloned by the host is 14,000 something, but within the child thinks that it's PID 1. And this is essentially what you get when you do this as well. So if you run a container, this is the Docker container, but it doesn't matter. If you run this container here, and you do ps-ef as the only process within the container, then it will show you that he thinks he is PID 1, and that his parent PID is 0, so that he is the only process running on top of this kernel. And this is the basic usage or the basic magic behind Linux containers in all of the different namespaces, and we have a couple of them there. So PID, as I showed, is just the process ID table. Then we have a network namespace so that you have your own IP stack, a mount namespace which gives you your own file systems, an IPC namespace which provides you IPC, so inter-process communication. UTS is the oldest one, I guess. It's the Unix time-sharing namespace, which gives you a NIS domain, which you might not need anymore, and a host name. And the user namespace is the more recent one, where you can say that no matter which user you are inside of a container, outside of the container, you are user X. So let's say you are user whatever, user. And inside of the container, you're root. If you touch a file, then this file will appear as user, because you told the container to be in the user namespace for user. And then there are one one new one, C group namespace. So if you deal with C groups in version 1, there is a C group version 2 coming. So I'm excited to look into this, but for now it's not, we don't have time. But for C groups, you need root privileges, and they introduce a new namespace that deals with this abstraction or isolation of the C groups handling for containers as well. And last year, Mellanox provided an RDMA namespace. I haven't tried it out because I'm not in the HPC business anymore, I guess. It's fair to say, it's just my interest. And I don't have had time to look into this, but that would be cool as well, to have like an RDMA namespace where you can abstract the different or multi-tenant access to the Mellanox or to the InfiniBand card. And you do not need anymore this SRIOV where you have multiple virtual devices to attach to different guest systems. So with this, it should be possible that you can run ad hoc, you can run containers, and then the resource scheduling and the resource monitoring will be done by the kernel instead of by this virtual functions. But it's to explore. And if you start a container, normally it will get all the namespaces that we have here for each container. But what you also could do is you can share namespaces between different containers. And on the container 4 side, this will look to you like a virtual machine, so you can think of it as a virtual machine on steroids. But this virtual machine on steroids thinking breaks when you share namespaces, right? And the resources can be restrained or restricted by using C groups, but I won't get into that. So if you run a container or if you run multiple containers and you do not constrain how much resources they can consume, each of this container can get all the resources of the host. So maybe container 1 runs a big job and gets all the CPU resources, and another one wants to get this resource as well. They have to compete as if they would run on the same system because they are running under the same kernel. So the kerneling, the scheduler of the kernel is the one that decides how much resources each container gets or each process gets. And this looks quite familiar, I guess, because the first namespaces entered in the very early year, 2002. And the thing is, you do not recognize this because on a normal host, you have only one namespace used, and this is, all the namespaces are the namespaces of the host. And if you fork a process on a host, you will get the same namespace as the host gets. That's just as it is. And if you run a virtual machine, because you have your own kernel inside of the virtual machine, as I showed before, you will get namespaces within these machines as well. So it's just transparent to the user. But with containers, you can spin up containers like this, and as I showed, you can share namespaces between containers. But what you also could do, and this is also very nice, you can share namespaces between the host and the container. And this is maybe a little bit scary, so. Oh, it's scary, but for DockerFor Mac, you need a virtual machine, right? Because containers are Linux namespace bound, so on the Mac, we don't have Linux, so I need an Alpine Linux or a Linux virtual machine on top of that. So I have the client version, which is Darwin, so the Mac version, and this Docker daemon inside of the virtual machine is a Linux machine, so I can run Linux containers. And if I do Docker run something and run a process, then the Docker client will connect to the Docker daemon, which will instantiate a container, and then I'm in the container, and this is how you run a container on a non-Linux system. And now if I want to get all in, so to speak, so if I want to go into the namespaces of the host, I can do this, but if you're easily scared, maybe you want to look away because this is looks scary, you can just use all the namespaces that I showed before and run this command like this. And with this, you will get privileges to all syscalls. With this, you won't be constrained by any syscall, so this is like seccom rules. Then I use the host PID namespace, I use the host UTC namespace and IPC and net namespace. What I cannot use is the host mount namespace, so I will just mount the host's root file system underneath host inside of my container. And when I'm in the container, I just change root to host, and now I'm completely within the host system. So as if I would be a process that is spawned under the host system, because I use all namespaces of the host, which is like SSHing as root into the host. That's what it is basically, or what it appears like. So so this is what you can do. You can share all the namespaces with the host, and then you're on the system without SSHing into it. but maybe I should. And if I then do change to a user that was not in the container, but was only on the host, then I also showed that I can change the user and I'm not constrained about the user namespace. Anyway, that's kind of scary, so I will skip this slide. The benefits of containers are packaging, so you can package the container once, and then you can run it everywhere. So everywhere means on all Linux systems with a recent kernel. You can distribute this container everywhere, and it's reproducible distributed, because you can, and this I show here, so each container that you download or upload will get a hash, a SHA hash, which is kind of like a git commit hash, and then you can pin this specific image within a child of this container. So you can tell, I would like to use this Alpine Linux container with this specific ID, and then you can make sure that you get the very same container for your application. And if you install some solver like OpenFOAM or whatever, then you can also provide this SHA hash in your thesis or in a paper, and everyone is able to reproduce exactly what you have done, because he makes sure that the file system and the metadata within the container is the same when you use this repo hash. It's simple to use. I mean, the kernel has Linux containers like for a couple of years now, for over 10 years even, and it was usable with LXC and zones and jails, but Docker brought it to the masses because they focused on making it easy to use, and I think that's their contribution to the Linux container ecosystem, that it's gained in momentum because it's so simple to use. And you get monitoring and auditing for free. So as I said, the C groups are there to constrain the usage, but you can only constrain usage if you keep track on all the resources that are used by the container. So the kernel namespaces also have counters like how many CPU shares are used, how many block I/O is done, and all these namespaces have their own measurements. And you can get this measurement for free if you ask the Docker daemon to provide you, give me all the stats of this container. And the goal is to only have one process in the container, so not use it as a virtual machine, but only spawn your solver. And with this, you can get for the solver a very clean and very neat metrics output, because it's only the process that you want that you started that will be measured by this container logs, right? So if you have only one Java program or one solver that's running in a container, you will get exactly the statistics of only this container without any noise from the system, because it's measured by the C groups and the namespaces. And you can also forward logs, so standard out, standard error of the container to a central logging facility, and then you get clean logs of the container as well without any noise of the system, which is pretty neat. And also what I talked about here at the HPC Advisory Council as well is that you can hand tailor user lens. So what we saw today and yesterday was that everyone is trying to compare apples with apples. So you have a CentOS 7 on your host, and you have a CentOS 7 in a virtual machine, and you try to compare how fast you can get, or how close you can get to the performance of the host. But what you can do with containers is you can optimize the user length for a specific use case. And I think this should be done more and more in the future, that you compare generic and optimized user lengths. So what I've done in 2014 when we were in China, I used a very alpha-ish version of CentOS 7 on the host, and I used a very mature version of CentOS 6 in the container. And what I could show was that the native version and the container with CentOS 7 were similar performance, but the more mature version of MPI and all the libraries within CentOS 6 were significantly faster than the bare metal host. And then I run HPCG, and I got like 10% or 20% gain in HPCG performance running Ubuntu over CentOS 7. So because you're only interfacing with the syscalls and you have your own libraries within the container, you can just throw out what you don't need inside of the container and make a very optimized user length for your application. So I think this should be explored more, because I'm not a benchmark guy, so I use the defaults for this benchmark, so maybe it's not the best benchmark here, but I think the trend is obvious, right? And this is 2 years old, or 2.5. So we should look into this more, or you should look into this more. Containers for software development, this is, I think, also very important, that if you are a software developer and you have to use a very complex stack, like use Elasticsearch and MongoDB and Memcached and whatever, with containers you can just start your environment that you want to develop against in containers and then just develop your application. Maybe even also within the container, but you can just spin up the stack you need and you don't need to spin up 10 virtual machines with all the overhead involved. You will just spin up the process that is needed. And this makes it very easy to develop against complex systems. And I think it's fair to say that like Python's virtual env boosted the Python development because you could just specify the packages you wanted to have in your Python environment. Containers also boost the complete environment or development environment because you can just specify for this development you need this service and this process. This is then spun up inside of containers, so it's very reproducible, as I showed before, and then you can just interact and develop against this service that you just spun up. Okay, so far, generic Linux container questions, or everything's clear? Okay, then I will go on. So now we are looking into specific runtimes. So before we were just looking at the special, or as a generic Linux container world. One of the widely used, I guess, runtimes, fair to say, because Docker has a very big market share there, is runc. So runc is the underlying runtime that Docker is using to spin up a container. It's a very low-level runtime. You need a JSON blob that specifies how the namespaces and how all this jazz is to spun up. And then you provide them with a targz or a directory where the root file system of the host or of the container is. And then it will create a container. And it's not a daemon that is long-running. It's just runc run, and then it will be interactive, and it will run as long as the container is running. So it's not that you need a Docker daemon, Docker engine to run a container. Then we have Rocket, which is from CoreOS. And this is both share something, because for instantiating a container, you need to be root, because you have to create the image, you have to mount a loopback device, you have to do certain things. You have to configure C groups, and for C group configuration, you also need privileges, so you cannot run this runtimes as normal user. I think this is one of the issues we face here in HPC. Rocket is basically the same as runc, but a little bit more, so it's not only running the container, but it's also downloading and verifying the image, and then it starts this app container. They call it app container on Rocket. What we saw yesterday from Greg was Singularity. This is more the approach of share everything so that you have the same user on multiple machines. And I guess it's fair to say that Singularity tries to aim to integrate in well and proven and existing share everything workflows. So it's not an orchestrator, and I will have this on the next slides as well. It's not an orchestrator, it's not a clustering system, it just fits into the current way of HPC workloads. And then we have also this is pluggable, this runc, so you can run Docker with Rocket or another runtime as well. And there's one interesting runtime worth mentioning, it's runv, which is a share nothing approach. So you have a hypervisor-based runtime, meaning you just start a kernel for each Linux container. So you start a virtual machine with the kernel, and then the container is hooking to this virtual machine's kernel and not to the kernel of the host system. So you have a share nothing approach, a hypervisor in between your container and the host system. Okay, and starting a container it's nice, but what you want to do is you want to start a container and start other containers. So you want to start multiple containers on a host, right? So with runc, you need to have the Docker engine in place, and beneath the Docker engine is the containerd framework that uses runc. And for Rocket, you can plug it, as I said, into Docker engine directly, or you could plug it in the Docker engine, or you could use it directly to just start containers on your host. For Singularity, as Greg showed yesterday, you need to create a container and then you can start it interactively. So it leverages current workflows like a bash start script, basically. And once you have done this on one host, you want to cluster it. So you want to spread it across multiple hosts. For Docker, the Docker ecosystem, there's SwarmKit. So SwarmKit is just a way of clustering multiple Docker engines on multiple hosts and let them interact together. For Rocket, we have multiple implementations, so you can plug Rocket into Kubernetes, and I think Kubernetes is well known, maybe under people that experienced a little bit Linux containers. Then you have Nomad, which is from HashiCorp. And you, as I said, you can also run Rocket underneath containerd and then run it as a Swarm cluster as well. So you are not tied to use runc here. And Singularity, as we saw yesterday again, it uses Slurm or a normal cluster manager to be clustered across multiple nodes. And it's just, I mean, it's an application wrapper around the application in essence, right? You just have to change your application so that it runs in a Singularity container, and then you can schedule it with the normal ways of scheduling things. Okay, another slide about orchestration. So there's also a word that you hear everywhere, that's Mesos. Mesos aims to be a distributed system kernel, meaning they are not targeting to be a container scheduler. They are more an operating system that spans across a complete data center, hence the name datacenter OS. So they are scheduling RAM, memory, and CPU and I/O. So like really a distributed operating system. And you can run then Swarm or Kubernetes on top of this scheduler, or you can use Marathon, which is a mechanism they implemented in Mesos to schedule containers on a cluster. But it's a much deeper layer than the other orchestration tools that I showed before. And Kubernetes, it stems from the container framework or the scheduling framework within Google called Borg. And I think it's fair to say that it matured to be the go-to orchestrator for services. So Greg yesterday said that containers are microservice virtualization, and I think partly it's true due to this Kubernetes fuss that you can schedule a service across your cluster and you can scale it across your cluster. So it's for services, and it's not done for HPC workloads. So maybe this is why he called it microservice virtualization, even though it's much more. Anyway, and then we have Swarm, which goes in a similar direction. So you can have you define services within Swarm, and then Swarm will make sure that a certain container is scheduled on nodes to run your service across multiple systems. And you can reach this service then with a load balancer that's also implemented in Swarm. And if I had more time, I would show it, but I have to carry on. And then we have status quo friendly, as I call them, like this share something, share everything approach. There is Shifter. I haven't heard from Shifter a couple of months now, but what it does, or what it did back last year, was it extracts the Docker image into a SquashFS, and then it changed routes into this SquashFS, which is not sure if you can call it container technology, because change route is not a container namespace, but that's what it did. Singularity, again, don't need to talk about it too much. I think Greg explained it yesterday very well. But what we also have is the share nothing cluster, right? So the cloud, like Amazon, and there is a nice talk about the latest announcement they had on the reInvent 2016. They have very beefy systems now as well. They have a Skylake instance with 2 sockets and 27 CPUs and a lot of RAM. They also provide now their own network adapter that they come up with, so their own interconnect, which is low latency and high bandwidth. So I mean everything you say about elastic or network adapters when you introduce them. They also have elastic GPUs, which is also cool. So you could come up with an instance, and when you need GPUs attached to this instance, then you can just add them as volumes, as you add volumes. So you add a GPU, and then you detach the GPU, and then you just pay for the usage that you for the time you attached it. Also cool. And they have, which is also very nice, Snowflake and Snow Mobile. Snowflake is just looks like a NAS. It's a box where you have 100 terabytes of storage that has this S3 interface, so you can push and pull data into it, and you could cluster it even so that you have like 10 of those, and when one is filled up, then you send it to Amazon and they will put it in the cloud. And Snow Mobile is not this NAS version, but it's a standard container with 100 petabytes of space. So if you have a lot of data you want to store, you just order one of these Snow Mobiles, put 100 petabytes in there, and then send it off to the cloud. Also a cool idea. And then they introduced AWS Batch, which is a batch system that you can use to schedule workloads. So it's like a resource scheduler on the cloud. Haven't used it, but it sounds interesting. Okay, and now a little bit broader. We have to look at the different iterations or the different questions or problems that are solved by Linux containers here, right? Docker solves the problem of speeding up the development cycle. So when you're on your machine or on a workstation or on a or maybe on a system in your data center, but only a single system, it's easy to use Docker or Docker Compose to spin up the environments I talked about, so and develop against them. And then you can do this CI/CD pipeline or the CI/CD cycle where you just try something out, and if it fails, then you trash everything, spin it up again, and as Docker is or Linux containers are very fast, you can trash it and spin it up in seconds, and then you iterate on it very fast. But once you want to go to a more distributed way of doing things, either it's an HPC system with everything shared, or just a share-nothing approach like a virtual machine system in the cloud, which could be Amazon or your own OpenStack in your data center. Then you have a problem because you have this distributed workload that you want to run, and it's not easy. For the services that, like running a web server or running a database, you can easily use Kubernetes or nowadays Docker Swarm to spin up those things. But for HPC workloads, it's much, or you can even use the AWS ECS, so Elastic Container solution that you can run your Kubernetes or your scheduler for containers in this service approach, or you can use Google's compute engine to run Google's container engine, which schedules your containers using Kubernetes as well, so that's a paid offering. But when you want to go to an HPC system, it's much harder because due to this distributed MPI workloads, you have to have the user available via SSH and reachable via SSH on the remote system, and this is not easily done in containers. I mean, you can spin up an SSD agent or SSD daemon within your container, but that's really not a good, sane approach to containers to do so, because it's not a virtual machine, and you shouldn't have multiple services within those. So that's kind of a pity. But with Greg's Singularity and a traditional Slurm, you can just run your workloads within certain Linux namespaces and be happy for the time that we need to wait until everything comes together. So as I said, development environments, they are easily done by containers. It's very cool. For non-HPC software development, it's pretty nice, and it's highly adopted in all over the place. But for HPC systems, it's not the case. I think one thing is that software development is maybe not the focus here. It's more iterating on the job settings and on the input data that is important for HPC systems. And the operating system, as I showed before, is different. So we have share everything against share nothing, or local systems against clusters. And I will go, because I'm a little bit over time, so I will rush through this. So Docker focuses more on the developer and not so much on the operations. Kubernetes focuses on the operations and not so much on the dev, because if you want to run a Docker container in Kubernetes, you have to squeeze it into a Kubernetes definition, which is a little bit different than running it on your local host, so there's a barrier. You can now use Swarm to run the Docker images clustered, but for HPC, as we have this Swarm workload managers, they are focusing on ops. Singularity tries to implement this DevOps style for the distribution and portability into HPC. And when you put them together, this seems like a good idea. It's a good idea, I think, for the time being, because the others don't care about MPI and HPC workloads yet. So this is a good fit for now. But what if MPI becomes container ready? That's one thing that would be nice. So if you run slurmd, for instance, it will, when you spawn a job, then slurmd will spawn the autod as a process, right? If this slurmd process would spawn it as a container, then we would be quite far and have containers in HPC, but we just spawning as a process, so that's kind of a thing. And even better is the container runtime would know about MPI workloads and try to implement this, then it would be cool as well. And ideally, the container engine and the clouds, 2 minutes, okay, they would understand the MPI so that you can run, take your credit card, go to AWS, spin up your container cloud there, and then run your container workloads in the cloud because they know about MPI and the challenges in HPC, but we are not there yet. Okay, so this is like my free startup idea, and you can get rich fast, hopefully. Not rich, but dollar rich. Yeah, and that would be I have some backup slides, but I think we don't have time for backup slides. So yeah, if you have questions, so I'm very happy to answer. And at lunch please grab me throughout the conference so I can interact with you. I proposed a workshop about containers in the ISC in Europe, and I hope that I have a whole day so that we can go through all the challenges and all the different aspects, because it's like I could talk for days, I guess, or at least hours. Yeah, so thank you, and questions?